Alright, my students, welcome back to transport number, the last module or the last section for this module, transport number. We'll look at transport number, look at how to determine transport numbers. One of the methods is hit-off method. Look at the principle of the hit-off method. The second method is the moving boundary method. Look at the principle behind moving boundary method. Then look at an illustration and we'll conclude. Now, transport number is defined as a fraction of the total current carried by each of the ions present in solution. So, for example, if you have cation and anion, we can measure what fraction, what quantity of current is carried by the positive ion, or what quantity of current is carried by the negative ion. That gives us the transport number. The quantity of electricity, Qi, carried through a unit volume of solution by ions of the ith kind is proportional to concentration, the charge Zi, that is Ci here, Zi, and the mobility. Therefore, we can say that Qi is equal to K is a constant, Ci, Zi, and Ui, where the proportionality constant includes the time, that is, takes care of the time factor. So which means the total will be equal to C1, Z1, U1 plus C2 plus, if there are still other ions. So which means we have K summation C1, Ci, Zi, Ui, from limit of I to the maximum, that is the total number of ions in the solution. Therefore, Ti, which is the fraction of current, will be equal to Qi divided by Q. So that means, if you're saying Qi, it now means Ci, Zi, Ui divided by summation, that is the total of what is there. This fraction is the transport number. And transport number is also called migration number or interference number, like I said. So if you can transport or migrate from one point to the other, so there is something that person is transporting. For the simplest case of a single electrolyte yielding 1:1 salt, T plus is this and T minus is equation 4.20b. If you look at it, the only difference here is for T plus, C plus, Z plus, U plus is a numerator, and then here is C minus, Z minus, U minus is the numerator. The denominator here is the same. That is the total for the positive and negative. The total for the positive and negative. However, C plus Z plus will be equal to this because we say it's 1:1. Says the solution must be electrically neutral. Therefore, transport number, what is remaining now is the mobility over the mobility of positive ion plus negative ion, and that of negative ion will be mobility of negative ion divided by total mobility. And the sum of transport number must be unity, that is T plus plus T minus must be equal to 1. Again, since lambda plus minus is this, we can also write this in terms of the transport number. And knowing that this is the same as lambda plus minus, if we cross multiply, then it means that lambda plus minus will be capital lambda multiplied by T plus minus. That's how we got this. Therefore, if we have independent way of measuring transport numbers, then the individual conductivities and mobilities can also be established. We have the hit-off method. And this method, when we see the diagram, it will become easy to explain. That if a solution, we have M plus, A plus, that is for Ma, we ionize as M plus. Now, if it let's make it univalent, that is 1:1. For it to be easy, the fraction of the currents will be T plus and T minus. Then we'll bring in the Faraday. 1 Faraday is 96500. So for positive the electricity pass will be 965. You see the fraction as a transport number multiplied by concentration, and this is for negative ions. Now at the same time, 1 mole of each is discharged at the electrode. Remember, that movement is what happens towards the electrode. So when it gets to the electrode, 1 mole will be discharged. Now if the cell containing the electrolyte divided into 3 compartments, we are trying to look at one towards the anode, the middle compartment, and the one, towards the cathode. Now let's look at that diagram for more explanation. Look at what it means here. Look at the heat-off method, middle compartment, anode compartment, cathode compartment. This is where we have the solution. This we have sketched here. Look at what is happening. There's a transport of A minus and then transport of T plus this way towards the right and A minus towards the left. Remember, negative ions go to positive electrode and positive ions go to negative electrode. So this is what is happening here, is what we have sketched here. And at the electron there will be net loss of 1 minus T minus, which is equal to T plus of A minus. And now the loss of T minus plus. In the middle there will be no concentration change, because what is moving this way is the same that is moving in the opposite direction. So at any point, no concentration change in this middle here. Now let's look at the results. At the anode, we have mentioned that. At the cathode, the same thing, loss of 1 minus T plus. Remember that T plus plus T minus was equal to 1. So 1 minus T plus will give us T minus. Therefore, moles lost from anode compartment divided by moles lost from cathode compartment is equal to T plus over T minus. Since T plus plus T minus is 1, then we can get the values of this and calculate. Alternatively, we can use the moles lost from anode compartment divided by moles deposited is T plus, whereas moles lost from cathode compartment divided by moles deposited is T minus. And from there we can calculate the transport number. Now another method is the moving boundary method. And this moving boundary method we will explain using a diagram too. We have the apparatus, lithium chloride, this is supposed to be lithium chloride, then with hydrochloric acid. The bottom line here is that we need to establish a movement boundary where we have what is called the moving ion and the following ion. And once we have that movement, we will be able to calculate the movement of the ion, that is the conductance, the conductivity, and hence we can get the transport number. Look at the diagram for the moving boundary method. The sketch is here, anode, cathode. Look at this B prime, A prime. So we have M plus and M prime plus. These ions will move. They don't have the same mobility. So once this is moving, this is following it to give us this distance from here to here. The same thing happens here from here to here. That's what happens here. Lithium chloride plus methyl orange, which gives us that color to show the difference. And this one is HCl, and methyl orange also gives us the difference in the following ions and the moving ions. So from there, let MA be the electrolyte for which transport number we're trying to move. Now we have another one, M prime A and MA prime, which indicates we call the following ions. So if you put that in that electrolysis tube we have seen, as the current flows, the boundary remains distinct. These ions cannot overtake these ions, and we have a boundary. Also, this cannot, A prime cannot overtake A minus, and we also have a boundary. Like I said, the slower ions are called the following ions. They are following the ions we want to measure their transport number. So once we establish these boundaries, AA prime divided by AA prime plus BB prime is T plus, and BB prime divided by AA prime plus BB prime is T minus. Now alternatively, we can follow the quantity of electricity that is passed through the system, T plus Q or T minus Q. Now if C is the concentration for the positive ions, we'll have these ions occupy the volume base, which is equal to this. Remember, this is dm, we have changed to cm, that's why you're seeing this 1000 here. And this volume is A multiplied by that distance it has moved, where A is the cross-sectional area and this is the distance through which the boundary moves. Therefore, this AA prime multiplied by the area is equal to that. That means T plus, we can make the T plus the subject and we can calculate the T plus. So we know, using our definition for Q, we can always calculate Q, and when we put it here, we can now using monitoring the progress of the boundary to calculate our transport number. This is an illustration. Transport number of hydrogen ion and sulfate ion, and we are given the millimeter, that is the apparatus, the tube, and then we are given the concentration, and this is the advancement of the boundary. We are told to find T plus and T minus. We state the equation where Z plus is 1. Now A for the circle is pi r squared. So we have our r, we calculate. This is the diameter divided by 2 gives us r, so we square and convert to meter squared. So we now substitute in that equation, this equation here. We are going to calculate x over t. So calculate this table, x over t, and that's what we have here. If you plot a graph of this, you will get an average. But if you don't want to plot a graph like we did here, we'll take an average of these values. 215, 215.3, 215.5, 215. Sorry, this is 215.6 and 215.5. We'll take an average and we'll get this 215.4. We'll now change in millimeter per second and we'll substitute. Once we get the transport number of the sulfate ion, we can now minus from 1 to get the transport number. Once we get the transport number of hydrogen ion, which is this, we now do 1 minus this to give us the transport number, excuse me, of the sulfate ion. Yeah, thank you very much. We looked at transport number, determination of transport number, the two methods, digital method and moving boundary method. Thank you very much, and we've come to the end of this module. We expect to see you when we start the next module. Thank you very much.